Welcome back everyone to this lecture on activation functions. So recall from our neural network models that inputs X have a weight assigned to them W, and then we also add in a bias term attached to them in that perceptron or neuron model, which means as a formula we have the input X times W plus B. So clearly, if we start thinking about this, W just implies how much weight or strength we should be giving to that incoming input. We can almost think of it as kind of how important is that input. You can imagine that if we have a absolute value of that weight being very large, that input or that feature is probably really important. We can also think of B as an offset value. We mentioned this before, but basically that makes it so that X times W has to reach a certain threshold before having an effect and overcoming that B term. So for example, if we have B is equal to -10, then the effects of X times W won't really start to overcome that B or bias term until their product surpasses 10. So after that, then the effect is solely based on that value of W, thus the term bias for B. So you can essentially think of that bias term as a threshold that the neuron has placed in order for the input times the weight to start taking some sort of majority effect. So next what we want to do is we want to set boundaries for the overall output value of that combination X times W plus B. And to keep things simple, what we can do is we can state Z is equal to X times W plus B. And then we can pass that term Z through some sort of activation function to limit its value. Now keep in mind a lot of research has been done into activation functions and their effectiveness. We're going to explore some really common activation functions, and then I'll also show you the Wikipedia page for activation functions, which displays and lists a lot more. So recall the simple neuron or perceptron model has an f of x, so we have those x's times their weights plus the bias of that neuron. So you can imagine if we had a binary classification problem, we would want an output of either 0 or 1. Now as a quick note, as I mentioned, to avoid confusion, I'm going to define the total inputs as this variable z, where z is equal to wx plus b. So in this context of a neural network and passing in the inputs times the weight plus the bias into an activation function, I'm really going to pass in that z term into the activation function. Keep in mind you often see these variables capitalized in the literature, such as function of capital Z or function of capital Z in regards to some capital X, to denote that instead of a single X input, you actually have a tensor input consisting of multiple values, which means Z is also a tensor, which means you have a tensor of weights, etc. So don't get confused on the capitalization you may see if you're reading some books. Another thing not to get confused by, often when people are writing out these activation functions, it's just really common practice to write them out in regards to F, since writing a function in regards to X is kind of the default. So you may see some activation functions written out in regards to X, especially on that Wikipedia page, or just in normal literature and books you're reading on deep learning. Don't let that confuse you. We're actually passing in Wx plus B in its entirety to the activation functions. Okay, so I just mentioned if we're doing a binary classification problem, it would be really nice that the neuron always spits out either a 0 or 1. So the absolute simplest networks can rely on a basic step function that outputs 0 or 1. So all we do is dependent on the value of z along here, we can see the x-axis. What we're going to do is if its value of z is less than 0, we output 0. If value of z is greater than 0, then we output 1. So regardless of the values, what's nice about this, it's always going to output 0 or 1. So this sort of function is really useful for classification. It will always output either 0 or 1. However, this is a very quote-unquote strong function, since really small changes aren't reflected. You can see here, there's just an immediate cutoff that splits between 0 and 1. If the total output of z happens to be less than 0, we just define that as 0. If the total output of z happens to be greater than 0, then when we pass it through this step function, we kind of top it off at 1. So there's a floor at 0, a ceiling at 1, and the immediate cutoff just depends on what that total value of z ended up being. It would be really nice, however, if instead of using such a dramatic step function, we have a little bit more of a dynamic function. For example, that red line. So lucky for us, and you're probably already familiar with this if you've done any machine learning classes, this is actually the sigmoid function. It has the same lower bound and upper bound, so 0 and 1, which is useful for binary classification, but it does this in a little more of a moderate fashion than a simple cutoff that a step function would do. And here we can see the formula for a sigmoid function, also known as the logistic function, which is f of z in our case is equal to 1 divided by 1 plus e to the power of negative z, where z in our case would be equal to wx plus b. So changing the activation function used in your neurons can be really beneficial depending on the task. Now keep in mind this still works for classification, but what's really nice is it's going to be slightly more sensitive to small changes. And if we want, we can actually grab that output of the sigmoid value to then treat it as a probability between 0 and 1. Since we can see here that there's actually values that it's going to output between 0 and 1 instead of solely 0 or solely 1. That red line is going to be able to report back something like 0.6 or 0.4, which should then give you an idea of how sure the network is that it belongs into any particular class. So let's discuss a few more activation functions that we're going to encounter. So some really common ones are things like the hyperbolic tangent, written out as tan h, and here we can see the formulas with respect to x on the right hand side. So there's hyperbolic cosine, hyperbolic sine, but the most common one is hyperbolic tangent, which is hyperbolic sine divided by hyperbolic cosine. So what's nice about this is it's going to output between -1 and 1 instead of 0 to 1. Looks really similar to a sigmoid function. Essentially the main difference is that lower bound, that floor. And we'll discuss why later on with certain neurons and certain networks, it makes more sense to use a hyperbolic tangent. I just want you to be aware that it's a really common option. Now, another really common option is the rectified linear unit, shortened to RELU. And this is actually a relatively simple function. Basically, you can describe it as max 0, z, which essentially states that if the output of the value is less than 0, we treat it as 0. Otherwise, if it's greater than 0, we go ahead and output the actual z value. So rectified linear units have actually been found to have very good performance, especially when dealing with the issue of vanishing gradient, which is a term and issue we'll discuss in more detail in a future lecture. Because it's so common to use rectified linear units in literature, we're often, when we're building out our networks, going to default to a rectified linear unit as our activation function due to its overall good performance. Now for a full list of possible activation functions, I highly encourage you to check out the Wikipedia page on activation functions. In fact, let's go ahead and take a quick tour of it now. Alright, here I am on the Wikipedia page for activation functions. And we can see here that it actually shows you the logistic activation function as kind of its main image. But if you begin to scroll down, it talks about functions, talks about biologically inspired neural networks. So here's the image we were showing you earlier. You can keep going down here, some alternative structures if you don't want to use an activation function. But eventually when you scroll down here, it shows you some things to compare activation functions against, such as being nonlinear, the range, the upper bound, the lower bounds, if they're continuously differentiable. But here we can see this little table that displays a lot of commonly used activation functions, as well as their derivatives, which is going to be important when we're talking about things like backpropagation. But the main thing to keep in mind is really just the name, the plot, and the equation, which should give you kind of an overview of what the activation function is actually doing. There's a simple identity, which is just whatever the neuron outputs, that's going to be what it outputs with the activation function attached to it. There's the binary step, essentially 0 if you're less than 0, 1 if you're greater than or equal to 0. The logistic, otherwise known as a sigmoid or soft step, also very, very common activation function to use, especially for binary classification. We have things like the hyperbolic tangent, which we just mentioned looks a lot like sigmoid, except you can see here the upper and lower bound. Specifically, the lower bound goes to -1. There's arctangent, hyperbolic sine, lots of different things here. Then if you keep scrolling down, you see the rectified linear unit that has a whole Wikipedia page if you're interested in it. As I mentioned before, it's a really common activation function to use, so common it has its own Wikipedia article on it. Then there's kind of more advanced rectified linear units. So recently a lot of people have been experimenting with different variations off the rectified linear unit. Specifically, a really common one is this leaky rectified linear unit, which instead of kind of flatlining at 0 for values along the x-axis that are less than 0, it kind of leaks a little bit and has this really small gradient. This is actually a little exaggerated here. But you can see it's going to be 0.01x for x that is less than 0. So this is known as a leaky rectified linear unit. And there's a bunch of other linear units that you can check out here. So as you can see, we have lots of different options here, but typically what we're going to be doing is we'll be using things like sigmoid function, the softmax function for multi-class classification, which we'll talk about in just a second, and then rectified linear units, because overall they have pretty good performance. So keep that in mind. I encourage you to check out the activation function page here. This article is really interesting. But the other thing I would want you to keep in mind is right now we've only discussed things like binary classification, keeping things between 0 and 1. And then maybe we have some sort of fixed probability there. But there's another set of issues that we have to kind of think about if we're dealing with multi-class classification. So let's go ahead and discuss multi-class classification activation functions and networks in the next lecture. I'll see you there.